Thank you very much. Hello, everyone, and thanks for joining. My name is Ali Gilani, PhD student at EPFL. I'm here to talk about our Aptamer-Decorated Graphene channel array with liquid gating for sensing cortisol, which is a project that is joint collaboration between our lab at EPFL, NanoLab, and Extensio, which is a startup company, and the Shokoofeh hospital. So here I'm going to talk about why we chose cortisol as a biomarker, and then I will explain where we can find this cortisol, and then I will explain how these graphene FETs actually are working and how we can functionalize it with Aptamer and how we can validate the functionalization, and I will show you the results of the sensing that we have. So point-of-care devices are actually diagnose these biomedical tools that enable us to immediate diagnosis and testing, which can help us speeding up the process of the treatment and also healthcare system. These point-of-care devices can be implemented in different settings, from self-testing to hospital, that can be used by different users, from amateur ones or semi-trained ones, or even the professional ones at hospital. The markets of point-of-care devices is predicted to reach to $74 billion till 2030. So it's a very huge market. And but although this is a huge market and it is an ocean of financial opportunity, the psychological aspects of human beings receives less attention. Talking about psychological aspect, I'm going to talk about why we chose cortisol. The main reason that we chose cortisol is actually the stress. There are few stress-related hormones. The main of them is the cortisol, which is also known as the stress hormone. When the body is stressed, the hypothalamus gland of the brain exerted CRH hormone that stimulate the pituitary gland to secrete ACTH, and it forces the adrenal gland to release the cortisol. The excessive prolonged secretion of the cortisol can cause problem, which is called chronic stress, and in long term can cause very serious problems systematically on the body and different organs, from neural system, digestive system, cardiovascular system, and the rest. So how we can diagnose the people who are suffering from chronic stress? The rhythm of the secretion of the cortisol of each person is like that. The normal one is like that in the morning you have increased level of the cortisol, and then at the end of the day it starts to decreasing. But for the people who are suffering from the chronic stress, it can be like other way around, irregular, or it can be high at all the time. So to diagnose it, we need to monitor this cortisol level during the day, which is very difficult with the conventional methods. Of course, there are other interests for measuring the cortisol from other other disease that Cushing syndrome, Addison disease, and also there are also some fancy applications from export application, or also evaluation of the performance of employees of a company. But where can we find this cortisol? The cortisol can be found in almost any biofluids in the body, from plasma, serum, saliva, interstitial fluid, or sweat or urine. But which one is the best for us for detecting the cortisol? We have some criteria here which should be in favor of our sensing, which the biofluid should be less contaminated, more pH stable. We should have very good accessibility to this biofluid, especially for the cortisol detection, because the subject needs to be very calm without induce any stress on them, and it's the best to be able to extract this biofluid at rest. And the lag time of this cortisol from from secretion to reaching to the targeted biomolecule should be low. And the other factor that should be also mentioned is that this the working with this biofluids should be commercially like mature enough. So considering all these factors, interstitial fluid is the best option. So our solution for this problem is to develop a wearable device that is composed of two parts, one for the extraction or giving the access of interstitial fluid, and also the sensing part, which in our case is the GFETs that is functionalized with the Aptamer that enable us to monitor the cortisol level like during the day or during different time intervals, either sequentially or continuously. So for the electrodes, for the sensing part, we chose graphene. Graphene among all of the like 2D materials shows promising characteristic for the biosensing application. This graphene can be used as a transducer to be functionalized with different bioreceptors, from DNA to antibodies, to detect different targeted biomarkers from analytes, ions, and also cells. This material is biocompatible, relatively easy to functionalize by stacking, and also it has a very high surface area, and it can be directly functionalized, which is able us to increase the sensitivity. And also this material is potentially able to be commercialized. But how this graphene is working? Actually, graphene is a band gap material that when it is neutral, it has the highest, lowest conductivity, and it can be the conductivity can be modulated by the gating. Not only that, by having, I have to also mention that the point that we have the lowest conductivity and lowest current is called the direct point, which is the most sensitive part of this. And not only by gating to modulate the conductivity, we can also do that by adding some charges on top of on the surface of the graphene. Like it means that if we have the graphene with a certain direct point, if we add some negative, for example, negative charges on top of it, we should expect to see the direct point shifted to the right. And it is other way around for the positive ions. So if we add positive ions, it should go to the left. And this direct point is quite sensitive to changes in the ions. So it means that the graphene can be utilized. It's a very good option for the sensing application. But how can we implement it? For implementation of this graphene, we use this configuration. We have the graphene as a channel. We have two terminals, that one of them is serve as a drain, the other one serve as a source, and the gating is applied through the liquid by the reference electrode, which in this case is the gold one. And you can see the optical image of the device, and we have the black squares are graphene, and we have the gold as a terminal, and also the reference electrodes. It should be also mentioned that the golds are passivated with aluminum oxide to prevent from non-specific bind. And here is the CM image of the graphene, and you can see the boundary layers, the seeds, the boundary layers, and also the seeds, the better the quality of the graphene. And this is how it's going to look. If you sweep the voltage of the gate in the liquid, you have a decrease in the current, which is reaching to the point which is the minimum. We call it the arc point, and also it can be implemented in the configuration of the GFET arrays. So why we use the arrays? It helps us to maintaining a very stable measurement, because sometimes in the middle of the measurement, the graphene can be delaminated. And also by using array of the graphene, we will have we can use and apply lower drain voltages, which means that we can have a lower power consumption and higher sensitivity. The bare graphene without the functionalization is characterized in 1x PBS. You can see that we're changing the fluid like with multiple times, that the direct point has not changed, and it maintains its stability. Not only that, we check different chips and devices of GFET devices, and we saw that all of them more or less show the reliable direct point stability, and it can be a repeatable and producible device. These are all tested in with silver chloride reference electrode. And for the detection of the cortisol, we use the aptamer. Aptamers are chain of oligonucleotides that can be folded in a unit three-dimensional shapes that makes them very specific to certain specific targeted molecules. And when the binding happens with that specific target molecule, there will be a conformational change that we will use this conformational change later in our sensing. And it's also noteworthy to say that the aptamers are negatively charged because of their backbone that is like made of phosphate, and makes them negative charge. The advantage of aptamers that we chose them over antibodies is that they are smaller compared to antibodies, and it makes them a very good option for the smaller molecule detection. They have very high specificity and affinity, and they can be synthesized chemically. And compared to antibodies, they are showing very much more stable behavior, and you can leave them in the room temperature for a long time. And they can be produced very rapidly. But these aptamers also have some challenges. One challenge of these aptamers is like how they are gonna deal with this debye length. The debye length is the length that the electrostatic changes on the surface of our FET is gonna be sensed in the channel of the FET. It's very short, especially in the 1x PBS, and it's around 0.7 nanometer. And this debye length is highly dependent on the ionic strength of the solution that we are using. As I said, in 1x PBS is 0.7. There is also some challenges for the functionalization of them. They should be very well aligned so they can act all together to amplify the effect. And they are also very sensitive to ionic stress. So it means that if you develop an aptamer in a certain ionic stress, it's not guaranteed that it's working in diluted ones. So it's very sensitive to that, and it can affect the performance. And while we are functionalizing that, they can be agglomerated. So it is a bit tricky to separate them. And the other thing that should be mentioned for the aptamers is that it's not like that to have the more dense aptamers on your surface, the better the sensitivity you have. These aptamers needs a bit of space to move around to make these conformational shape changes. So the density of your aptamers on the surface is very crucial and should be tuned. Talking about them all, how should we functionalize our GFET? So there are multiple steps for the functionalization. We cannot directly functionalize the GFET, the graphene itself, by the aptamer. We need a mediator. Here we use P-base, which is on one end, it has an aromatic molecule that has pi orbital that can be non-covalently bind with the pi orbital of the graphene, and on the other end it has ester that can react with the amine that is tagged on the aptamers, and when they react, you actually immobilize your aptamers and your graphene. And when the binding is happening, it can go either going down or going up, or it can be locked in. With all these changes, it can induce changes in the voltage, current, and the capacitance in your substrate, which are in our case is graphene. So how could it be on our GFET, and how is this cortisol aptamer is working? So we use two type of aptamers. One is specific to the cortisol, and the other one is a scramble of that, which we call it non-specific to cortisol, to check the non-specific bindings. This aptamer, when it binds with the cortisol, it's moving upward, it's oriented upward. And by knowing that the aptamers are negatively charged, so when we have the negative charge on top of our graphene, we expect to have a bit of shift of the direct point to the right after immobilizing the aptamers. And when the binding of the cortisol with the aptamer is happening with our own aptamer, it is expected to create a bit of distance of the charges from the surface. So we expect the direct point going to the left. So after knowing this all, we carefully validate the functionalization of each step. For P-based one, we use Raman spectroscopy. In the literature, it's so common to use DMF, but DMF is not that graphene friendly, and it can be washed away during the rinsing of the sensor after the incubation. And it's a bit difficult to work, but here as an alternative, we introduce DMSO-methanol, which is more graphene friendly, and according to Raman, it shows better immobilization of the P-base on top of the graphene. For the immobilization of the aptamer on the surface of the graphene, we use the GFET itself. As I said, when we have the negative charge on top, we should expect to have the direct point going to the right. So we use some chips. We firstly find the direct point after carefully check the stability with different refilling and intervals. And then we also measure the direct point after the functionalization of the aptamer, and we could see that there has been a shift of the direct point after the aptamer functionalization. So, and for the binding of the cortisol, we use the AFM-SNOM. We did that in 1x PBS. We left incubated the graphene for 10 minutes, and then compare the AFM results before and after the cortisol incubation, and we could see some changes that most likely due to cortisol binding. Okay, after validating and carefully validating all the steps of the validation, functionalization, it's time to test our functionalized GFETs with the cortisol. So we did the measurement in 1x PBS, which is the closest option that we have to real condition in terms of the ionic strengths. And we started the measurement finding the behavior of the device in the buffer zone, which is like incubating with the control solution, which is 1x PBS without cortisol, and then starting to incubate it with the cortisol, and for 10 minutes with 15 macroliter of the sample, and doing the sweeping of the voltage of the gate and extracting the dark point. In the middle, you see the plot of the extracted dark points, that you can see that there is a bit of drift that might be because of the reference electrode, which is gold, that we use on-chip reference electrode. And after drift correction, you would see that there has been a change of the direct point, and as it is expected, it went to the left. And we did also a real-time measurement. And in this case, we just biased the voltage at the point very close to the direct point. Again, we started with the 1x PBS, which is the highest ionic strength that is in our favor. And after seeing that the sensor is stable enough, we started the incubation with the different concentration. It started from 1 picomolar to 1 macromolar, and You see that at the end, from 100 nanomolar to 1 macromolar, we reached a bit of saturation. And we could, after the drift correction that is coming from the beginning, we could reach to the sensitivity of 150 nanoamp, which is, I would say, it's a very nice result. And we could cover the range from 1 picomolar to 1 macromolar that cover the desired concentration region of the range, the desired range of the cortisol that we look for in the ISF. And at the end, as a conclusion, we successfully characterized the GFET with liquid gating, successfully functionalized it with the Aptamer, and we could achieve very, very good sensitivity of 0.154 macroamp per decade of the cortisol, and we could cover a very wide range of 1 picomolar to 1 macromolar. And the most important thing I would say is that it is working in 1x PBS. And so if you want to use it, there is no need to pre-processing of the sample. For the future works, we have to using the experiments that we gained to measure the ISF, measure the cortisol in the real ISF from the clinical samples, and lowering the volume of the measurement. And thank you very much for your attention. And if you have any question, I'm here to answer.